Good afternoon, everyone. Good afternoon.
Good afternoon, teacher.
Okay, yesterday we left off when I had just, was it the other day, when I had introduced molar heat capacity, and I promised to come in for gas changes. And among the changes we have we have what we call the isovolumetric process. 2, we have what we call the isobaric process. These are all processes that occur in gases. We have what we call the isothermal process. Now, in isovolumetric, we have what we call a constant volume. So ideally, isovolumetric is the process that takes place at a constant volume. Then isobaric is a process that takes place at a constant pressure. Then isothermal is that process that takes place at a constant temperature. So you'll see that the gas changes isovolumetrically. That means by using a process which has a constant volume, that the pressure of the gas may change or its temperature may change, but the volume may not change. That is why we are saying it's occurring at a constant volume. Then in isobaric process, the gas may change its volume, its temperature may rise or decrease, but the pressure may not change. Then lastly, we have the isothermal process, and in this one, the pressure of the gas can change. Likewise, the temperature, the volume can also change, but the temperature will remain what? Constant. Now, an isothermal process obeys what we call Boyle's law. If you're looking at an isothermal process, it obeys Boyle's law, where Boyle's law is PV is equal to a constant. And if PV is equal to a constant, then the graph representing pressure and volume takes such a shape, whereby we can have this as temperature 1, can have this one as temperature 2, we can have this one as temperature 3. So whatever happens along those curves, if it happens along this curve 1, then the temperature on this curve is T3. Wherever you are, whether you are here or you are there or we are there, it is occurring at a constant temperature. When you're on this second one, the temperature is T2, whether you're up here or there or there or there. Likewise, if you're here at T1, the temperature there, 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 and there along the entire curve is the same. So that is what occurs under what we call an isothermal process. The other ones, we shall not discuss much about them. We shall deal more with the isothermal process at this stage. And we can talk about the conditions necessary to achieve the isothermal process. Conditions to achieve the isothermal process. So if one wants to achieve the isothermal process, 1, the gas should be held in a thin-walled, highly conductive vessel. So the gas should be held in a thin-walled, highly conducive vessel sorry, not conducive, conductive vessel. Then the second one, the gas container or the vessel should be surrounded by a constant temperature bath. Gas vessel should be surrounded by a constant temperature bath. Then thirdly, the process should be carried out in slow steps to give enough time for the heat exchange so as to maintain the temperature. Process carried out in a slow process, in a slow steps to give enough time for the heat exchange so as to maintain the temperature. Because in isothermal, we have seen that the temperature has remained what? Constant. So with those conditions, we can now go ahead and talk about what we call the work done in expanding the ideal gas under isothermal process. Work done in expanding ideal gas under isothermal process. So with this, you can consider any moles of an ideal gas. These are n moles of an ideal gas. Enclosed in a vessel with a frictionless piston at a pressure P. P is the pressure in an enclosed vessel with a piston. If the volume changes by delta V, volume changes by delta V, then also work done will change by that. Work done would have changed by delta W. So, from small change in work done is equal to P times small change in volume. The volume changes from V1 to V2. Volume changes from V1 to V2. Then the work done will be equal to dW is equal to PdV. Then you integrate the work from work done is 0, work done is W, integrate the volume from V1 up to V2. When you integrate W with respect to 1 with respect to W, you'll get W from 0 to W is equal to integral from V1 to V2 of PdV. Therefore, work done will be equal to P V, but from V1 up to V2. I assume everyone knows how to integrate. Do you know how to integrate? I don't want to assume that someone does not know how to. That's why I delayed teaching this part. I wanted people to have good knowledge of integration. So with that knowledge of integration, we shall have V over V2 minus V1. Therefore, work done would would be equal to change in PV change in what? V2 minus V1. But also recall, PV is equal to nRT. That means if I want P alone, P will be equal to nRT over V. And with this, you can have wait, I think I've made a mistake here. I shouldn't have integrated yet. At this point, shouldn't have integrated because P can be expressed in terms of volume. So it would be equal to the integral of V1 to V2 of PdV. Now, when you substitute for P from here, you will have W, which is work done, is the integral from V1 to V2 of nRT over V dV. Fatma, you don't know how to integrate. When you're integrating, for example, x to the power n with respect to x, the answer is x power n plus 1 divided by n plus 1. If I'm integrating 1 dx, I get that very term because this is x power 1 is the same as x power 0. So it becomes x power 0 plus 1 over 0 plus 1. So the answer is x. Then also if you integrate, this one you've not covered, it's in Backhouse too. When you integrate 1 over x dx, the answer is natural log of x. So with that, when I factorize this out, I'll get nRT. Because temperature is constant, this is under isothermal. Temperature is constant, R is molar gas constant, N is number of moles. Then what will only vary is 1 over V with respect to V, varying from V1 to V2. So with this, we shall get work done is equal to, here I'll use this skill. When I integrate 1 over V, I'll get natural log. So this is nRT. Natural log is written like this, of V, from 1, V1, V2. Therefore, this will imply that we get nRT. When I write natural log in its fully form, it's log to base E of V2 minus log to base E of V1. But because these are logarithms, and most of your mathematicians, it's the same as nRT times log base E of V2 over V1. So therefore, one can finally conclude and say the work done under isothermal is nRT log base E V2 over V1. You find some books saying work done is nRT ln V1 V2 over V1. They are the same. So with that, you would have done the derivation of work done under isothermal process. Unless if people have questions. You have questions, raise them for that derivation. Then there is one type of process I didn't talk about. That type of process is what we call process number 4, which is called the adiabatic process. And for this system, or for this force, for this process, we are going to look at it as the force, as the process which does not allow heat, or is the process whereby heat is not allowed to enter or leave a given gas system. So if you have an enclosure of a gas, maybe if you have this bottle, and the gas is enclosed within this bottle, then the gas is not allowed to, one, allow heat to come in. At the same time, the gas does not allow heat to leave the system. With this system, or with this process, we say is experiencing what we call the adiabatic process. So by definition, this is a process for which no heat is allowed to enter or leave the gas system. So it's a process for which no heat is allowed to leave or enter a gas system. Sorry, not process. A gas system. No worries, all right, we'll send the writer. Then they can ask you for the conditions for the adiabatic process to occur. The conditions for an adiabatic process. To be realized, or to realize an adiabatic process, one, the gas should be held in a thick, the other one was thin, but here the gas should be held in a thick walled, poorly conducting vessel. When the vessel is thick, poorly conducting, it will not allow heat to come. It will not allow heat to leave. Okay? Secondly, the process should be carried out very fast. Process should be carried out very fast, i.e. rapid steps, so that there is no time for heat exchange. Okay? Now, adiabatic processes have their own definitions of formulae, just like you've seen for gas laws, for gas equations, and Boyle's law, Charles's law, and pressure law. In this case, the equations are almost the same, but because of adiabatic process and because of other definitions, you can see that adiabatic processes PV gamma is equal to a constant. We have always known PV as Boyle's law, but for this case, we are looking at PV in terms of adiabatic process. We have not allowed heat to leave, neither we are allowing heat to enter the system. That is equation 1 for adiabatic process. Equation 2 for adiabatic process is TV gamma minus 1 is equal to a constant. This is in line with what we have as Chalk's law, but this time around we have gamma minus 1. And if you remember what gamma is, who recalls what gamma is? We derived it last lesson. Who recalls what gamma is? Gamma is the ratio of molar gas constant at a constant what? Pressure to molar gas constant at a constant what? Volume. I remember talking about gamma as Cp over Cv. So if you did not make the notes or you did not go through them, you cannot know what I'm talking about. Then the last equation for adiabatic is pressure power 1 minus gamma T power gamma is equal to a constant. Okay, so with this, we have these equations which we need to derive. They can ask you to derive and show that for adiabatic processes, PV gamma is equal to a constant. Show that for adiabatic processes, TV gamma minus 1 is a constant. For adiabatic processes, P of 1 minus gamma times temperature power gamma is a constant. So we are going to derive these equations. I hope we can derive like 2. God willing. I'll start with PV gamma is a constant. The derivation for PV gamma is a constant. Now to start with, you should recall that from the first law of thermodynamics, which says that the change in heat energy is equal to work done internally plus external work done by the system. Yeah. Since no heat is allowed to leave or enter the system, the change in energy is 0. So the change in heat energy is equal to 0 since heat is not allowed to leave or enter the system. So with this, you realize that 1, the internal energy is got from NCV delta T, while from PV is equal to nRT, then T P itself will be nRT over V. Now, the change in work done externally is equal to P dV. So when I put here this P, I'll have nRT over V times dV. When you substitute up there in thermodynamics law, we shall have 0 is equal to NCV delta T plus nRT over V times dV. But also from here, if you look at this equation clearly, you would see that we have temperature is equal to PV over NR. So now I substitute here, I'll have 0 is equal to n CV delta T plus small n R over V. Because of our T, we shall have PV over NR times dV. There's something I needed to borrow from the other one. Okay. I should have first derived this one, because from here I wanted to quote that from this TV is equal to a constant, whereby if TV is a constant, then I can substitute here T. I think let me go back and first derive the other one, guys. I don't want to just quote it and then you ask yourselves, where am I getting it from? So I'll start from here. So I have to first derive. I'll have to first derive. I'll first derive TV gamma minus 1 is equal to a constant. Okay. External work done in this case will be by the system will be equal to PDV. It's PDV. We have seen that no heat is allowed to leave or enter the system. So it ideally implies that still change in energy is 0. So with the change in energy being 0, you have 0 is equal to N CV delta T plus P delta V. Having realized that, still you can make P the subject, but PV is equal to nRT. So P is equal to nRT over V. When you substitute for this, here we shall have N CV delta T plus nRT over V times delta V. Because of integration and differentiation, we can approximate the delta T to become dt, which will become N CV dt plus nRT over V dV. But remember, R is given by what? From the R is given by Cp minus Cv. You to recall, so we shall have this is equal to 0. So we shall have N Cv dt plus N of Cp minus Cv of T dV is equal to 0. I can divide everything by NCVT. And if I do so, this is what is going to happen. By NCVT divided by NCVT. I'll vamoosh the T there. The N here, the CV here. I'll remain with dt over capital T plus Cp over Cv minus 1 of dV is equal to 0. I don't know that people have seen what I've done there. I have divided this Cv with this one to create a 1. But Cp over Cv is the same as what? There is a volume I've forgotten. There was a volume here, so there is a V down here. So there is over V. So this will give me 1 over T dt plus gamma minus 1 over V dV is equal to 0. When integrate on both sides, we shall have integral of 1 over t dt plus integral of 1 over v into gamma minus 1 dv is 0. But because we are integrating on both sides, on integration we get a plus a constant. So the constant can go on the right-hand side. When the constant crosses on the right-hand side, the integral would have attained on that side. I can equate it to a constant, as I'm going to show you. So I can say the integral of 1 over t is natural log capital T plus natural log of v, the whole of this multiplied by gamma minus 1 is equal to a constant. So with this can be the same as log to base e, the same as log to base e of capital T plus gamma minus 1 of log to base e of v is equal to a constant. Furthermore, because they are logarithms, I can combine them as log base e of t plus log base e of v power gamma minus 1 is a constant. So finally, I can merge these two as log base e of t of v of gamma minus 1 is a constant. E is a number, the constant is also a number, so E of the constant is going to be equal to TV gamma minus 1. So finally, TV gamma minus 1 is always a constant. Hence we have proved equation 2 as per adiabatic expansions. Yes, Fatima. Fatima has a problem of integration. Yes, Fatima, go ahead.
Yeah. They are on the help repeat.
Where?
On the natural log T
Okay.
plus natural log V.
First of all, did you get to know earlier that integral of 1 over x dx, the answer is natural log of x?
Yeah.
So now integrate 1 over t, the answer is natural log of what? Of t, right? Now, after integration, is that what you're saying? Are you saying this line here?
Yeah. Yeah.
Ln is the same as log to base e. We just summarize this log to base e as ln, whereby it's ln. So I called it ln, but from logarithms, if I have a number, log of a power b power c power 2, the 2 can come forward, and I have log of a of b. Likewise, the 2 can go back. So our gamma minus 1 has gone back to gamma being gamma minus 1 power v. That's how it went back. Then we merged. This is product addition of logarithms. When logarithms are added together, they come in as a product. Okay? So with that, you can deduce that equation. So having deduced that one, it is now easier to deduce the other one I had told you about, which was equation 2. And for equation 2, still we can see that PV is equal to nRT, whereby T is equal to is equal to PV is equal to PV over R N. So the heat exchange is 0, or the heat change is 0, is equal to NCV delta T plus nRT over V delta V. This is the same as 0 is equal to NCV dt plus nRT over V dV.
Excuse me, teacher.
Yes, please. Yeah?
Teacher, I was inquiring why are we changing the. I was inquiring as to why we are changing the delta T, delta V into dt dV.
So that we can easily integrate it, because when they become very small, they come from limits in differentiation. If you have a curve and you have strips, those strips are changes in x. But as they become very, very small, they tend to be x. Change in x in the horizontal and change in y in the vertical. So as it becomes very small, the y delta x approximates to the y dx. Okay?
Okay,
So when
thank
I
you, teacher.
substitute here, I'll get
Yes.
0 is n cv dt plus n over pv times r over n r of v dv. So with that, we can divide r by this one, n by this one. Then we can also divide off the v. But before we can proceed with that, we can look at this part. If you recall, what we have just derived up there, from TV gamma minus 1 is a constant. I substitute here the t which I have seen here as this. I will have PV over NR times V power gamma minus 1 is a constant. But when you look at this, you'll have P times V power 1 plus gamma minus 1. This one dies with this one by subtraction. Over any r, and this is equal to a constant. Therefore, PV gamma is equal to nr times a constant. So for the same reason, PV gamma is a what? Is a constant. Now with this derivation, even if you did not start, unless if they say starting from heat energy or from changing from the first law of thermodynamics, that's how normally the question comes. So they require you to start from here. But if they don't ask you to start from there, you can start from here and conclude that. Then the last one. But before that, it means that P1, V1 gamma is equal to P2, V2 gamma. Likewise, T1, V1 gamma is equal to T2, V2 gamma minus 1. Let us deduce the third one before we can end the lesson. If I'm to deduce the third one, then next time we shall start on calculations. But before we start calculations, I need you to internalize them and make them sink in your heads by driving them again on your own. So the third one says, That equation says P power 1 minus gamma, T power gamma is a constant. So still from PV is equal to NRT, you can make V the subject because V is the one missing, which is NRT over P. Now from the first equation we derived of adiabatic expansion, TV gamma minus 1 was equal to a constant. So now I substitute, I'll have T times NRT over P power gamma minus 1 is a constant. Algebra here is needed. This T, there is a T power 1, there is a T power gamma minus 1, NR power gamma minus 1. It is a constant, you still get a constant, over P power gamma minus 1 is equal to a constant. This one can be subtracted off by that one. So we remain with T power gamma times. This one goes up, pressure of a negative of gamma minus 1. This NR can come down this way to give us a new constant. Therefore, finally,
Excuse me, teacher.
Yes, please.
Teacher, please repeat on the second step. This one.
On this the very last proof.
Yeah, the second step.
Okay. On the second, this one,
Yes.
I'm substituting for V. You see V is here, right? V has a
Yes.
power of gamma minus 1. So this part has to come and sit here. So it has sat there. Then you simplify. And hence you would have got the proof. So that means P1 power 1 minus gamma, and it's T1 power gamma equal to P2 power 1 minus gamma, and it's T2 power gamma. Here I have some few examples here I can talk about. Let me talk about one example before we leave. Any question on the derivations?
Teacher.
Yes, please.
In the conclusion.
Conclusion. If initially, maybe in the morning, the pressure of the gas was P1, and the temperature at that instance was T1. And in the evening, the pressure is P2, and the temperature is T2. Then for adiabatic expansion or process, P1 power gamma minus 1 times T1 power gamma should be equal to P2 power gamma minus 1. Sorry, power 1 minus gamma times T2 power gamma. Okay. those conclusions just confirm that if you consider a pressure, if you consider a vessel at a given temperature or volume or pressure, then after some time, you also consider it again, then you can investigate and see how best each of them can be handled. So we have that number as an example. It says the temperature of 1 mole of helium gas at a pressure of 1.0 exponent 5 pascals increases from 20 to 100 when the gas is compressed adiabatically. So that statement has to be mentioned somewhere of adiabatic expansion or compression. Find the pressure of the gas. Take gamma as 1.67. So they have given us initial temperature T1 as 20. Final temperature as T2 as 100. Yeah. The initial pressure P1 as 1.0 times 10 power 5 pascals. The final pressure P2 is what we are looking for. So we have seen the equation as P1, 1 minus gamma, T1 power gamma is equal to P2 of 1 minus gamma, T2 of gamma. So when you make the substitution, we shall have P1 is 1.05, 1.0 times 10 power 5 to the power. Now 1 minus gamma is equal to 1 minus 0.67, which is negative 0.67. So this is power negative 0.67 times 20 power 1.67 is equal to P2 we are looking for, power negative 0.67 times 100 the power, we had to convert the temperature. We are supposed to convert the temperature to Kelvin. So this is 200. Kelvin is 273. Don't so? So this converts to 373. Sorry, I have a headache which is disturbing me. So I'm a little bit forgetful today. This is 290.
293.
This is 293. This is 373 to the power 1.67. Can you put everything in a calc and get the answer? They are not so challenging questions to handle. Follow them very well. Someone press the kite and give us the answer.
Excuse me, teacher.
Yes, please.
Teacher, 1 minus gamma, isn't it 1 minus 1.67?
Gives you negative 0.67. It is not gamma minus 1, but 1 minus gamma. Eh? You get it? Eh? Now you have a problem there to compute with the calc. Eh? Especially when it comes to P, you have to introduce logarithms. So P is equal to 1 point times 10 power 5 power negative 0.67 times 293 power 1.67 divided by 373 power 1.67. So first compute the right hand side answer, then I show you how to introduce the log.
Two point.
The right hand side is 2 point.
2.9848 exponent negative 4.
Then if you introduce logarithms, this would be or you can raise it to a power. Eh? Multiply times power. So this side you have 2.98 times power negative 4 times negative 1 out of 0.67. So this will divide off and I'll remain with P. So that answer you've got, raise it to the power negative 1 out of 0.67.
One 1,000.
1,000.
182,000.
10 power 5.
182,524.
Is that the answer?
Yes, teacher.
Yes, teacher.
Okay. We can have that. Finalize, my head is not okay. I want to sum this lesson up. Shall start from there next time, guys. I'm going to send the right up.
Thank you, teacher.
Welcome. Okay, welcome, guys. Hope you done. I'm sending in the work.